In this lecture, basically, I'll be talking about uh, spin in rotating magnetic field, and then I will extend this lecture to. No, I mean to say that we will start with spin in a magnetic field, and this magnetic field is rotating, and then we will extend the same idea to a rotating frame of reference. So we will extend this idea to uh, uh, rotating frame of reference. So what we have is that uh, uh, so if I have to boil down the problem that I'm going to discuss, is that the first case that we'll be talking about is the spin uh, in a rotating magnetic field, and that is basically our laboratory frame of reference. So one is spin in laboratory frame of reference, and the next thing that we will extend this is to the rotating frame of reference. So in starting with, I will have spin in a rotating magnetic field. So what we have is we have a two-dimensional magnetic field, and a magnetic field in a plane. I can write down that as B, and this B can be written as B naught cos omega t x cap plus B naught sine omega t y. So this is my basis. This is my magnetic field in a two-dimensional plane, and then I'll start with the definition of magnetic moment. So if I go with magnetic moment of the magnetic moment of electron, so I have mu. This mu is, there's a relation between the magnetic moment and magnetic moment of the spin and the spin. That relation is minus E by 2ms. And E is the charge of the electron, m is its mass, and S here is the spin operator. And this spin operator can be written as, you can write down this spin operator, this S cap is nothing but, it is H bar by 2 sigma and I can write down the Hamiltonian. So what will be the Hamiltonian for this system? H will be minus mu dot B. And for mu, so H will be minus, for mu I'll be using E by 2m, then I'll have H bar sigma by 2 times B naught cosine omega t and x cap plus sine omega t y cap. So this is my rotating magnetic field, and this is my magnetic moment, and this sigma is the Pauli spin matrix, and we can write down for E by 2m, we can use gamma, what's called as gyromagnetic ratio. Gyromagnetic ratio. And and this H can be written as, the Hamiltonian can be written as minus gamma H bar by 2b naught and sigma x cosine omega t plus sigma y sine omega t. So this equation is self-explanatory, and you can reach out to this equation by inculcating the Pauli spin matrix. So this is my Hamiltonian for the spin in a rotating magnetic field. And obviously, this is a complex equation, and to deal with this equation is also complex, to evaluate those oscillating functions. But if I extend this argument that I make a drift from laboratory frame of reference to a frame of reference which is itself rotating, so I can write down the Hamiltonian for the rotating frame of reference. So Hamiltonian for rotating frame of reference. Okay. So this is my Hamiltonian in a situation where you have a spin. That spin is in a magnetic field, and now that's my laboratory frame of reference. But now what I'm doing is I'm rotating the frame itself. So I'm trying to translate my problem in a rotating frame of reference. So when I do that, I will have the Hamiltonian H dash. And let's assume this is H dash. This H dash will be U dagger HU minus IH bar U dagger du by dt. So this is our Hamiltonian for this system in a rotating frame of reference. The frame of reference is itself rotating, and the Hamiltonian for that system is given by this equation. Where this U is the time evolution operator, and this U is e to the power of I, say, omega naught sigma z t by 2. So now, when we think of rotating the frame of reference, we rotate it with respect to the z-axis of the problem. So that's why we have sigma z for u. So u equals e to the power of I omega naught sigma z t by 2. So what would I like to do is I would like to get my h dash. So the first thing here will be, let me go with this part of this equation. So I can evaluate this part by using u, and I'm using u like this. So this is my u. I can take its time derivative. So du by dt will be, so this is our exponential function. It will remain as is. So iota will be out, omega naught is out, sigma z is out, divide by 2 is out, and you'll be left with the same function, e to the power of I omega naught sigma z t by 2. All right, so this is how it goes. So for du by dt, I can use that in my equation, and what will I obtain from here? Okay, so I'll obtain h dash as for u dagger hu. I have already calculated what is that. That's minus gamma h bar b naught by 2 times sigma x cos omega t, and then plus sigma y sine omega t. Then I will have minus IH bar U dagger times What's that? That is I omega naught sigma z2. I omega naught sigma z by 2. And you will have your u again. So here you will have u again. Okay, so what we do here is we can average out the oscillating terms. We can average out the oscillating terms from this from the above equation, oscillating terms. And when we average out, then what we obtain is we obtain h dash. H dash comes out to be minus gamma b naught and sigma z by 2. And for this, we can see here, for this what we have is this iota, then omega naught sigma z is there, all right, and this 2. So what I'll have is I will have h bar omega naught sigma z. H bar, this will be minus h bar omega naught sigma z by 2. So what we have done is we have averaged out these functions, and on averaging out these functions, we have boiled down the Hamiltonian to a very, very simple form. And we can see that this h dash in rotating frame of reference. So we have rotating frame of reference. This h dash is what will be out. I think here I'm missing h bar. Here I must have h bar here. All right. So I can have this minus h bar out. I can think of sigma z out, and 2 is also out. So inside I'm left with gamma b, and it's b naught, then minus omega naught. So this is my h dash in a rotating frame of reference. See, the beauty of choosing the rotating frame of reference is that you have actually translated a dynamical problem into a static problem. You are moving from laboratory frame of reference to the rotating frame of reference, and this is automatically leading to the static situation where the magnetic field is not actually moving because the frame is moving with the magnetic field. That means this problem boils down to a problem of a nature in which your problem is boiled down to a static problem. And what we can do is we can use time evolution operator. We can calculate this. We can take a state psi, and this psi can be written as e to the power minus I h dash t by 2, then psi of 0. So the state of the system can be written like this, and the h dash is already calculated. And what's that h dash? Oh no, h dash. What's h dash? H dash is minus h bar sigma by 2, and this h dash is minus h bar sigma z by 2 gamma b naught minus omega naught. Gamma b naught minus omega naught. Your Hamiltonian is exclusively dependent on the Z component. It's only dependent on the Z component. So when we calculate the state of this system, and on using h dash in this equation, we come up with an effective frequency. Effective frequency. And what's that effective frequency? That effective frequency, if I represent that as E effective, this effective frequency, this effective frequency comes out to be equal to omega minus gamma b naught. And what we observe here is that when you have a rotating frame of reference, in a rotating frame of reference, the spin of this electron has an effective oscillation, and that effective oscillation is boiled down to omega minus gamma b naught, and revealing the fact that there is oscillatory there are oscillations. There are effective oscillations carried out by the system when we take into consideration the rotating frame of reference. And these oscillations, the effective oscillations that we calculate by solving this equation, using h dash given by this equation, what it automatically leads to, it leads to the oscillations, and these oscillations are called as Rabi oscillations. So to summarize this talk, what we started with is the problem is to have an interaction of magnetic field with the spin of an electron, and we treated out this problem on two accounts. The first account was choosing the laboratory frame of reference, in which actually you have a magnetic field, and this magnetic field has a dynamics in it, and that dynamics makes our problem very, very complicated. You come up with those oscillatory functions, but the moment you inculcate, the moment you think of using a rotating frame of reference, a dynamical problem that was in laboratory frame of reference, it automatically translates into a static problem when we choose the same choice for the rotating frame of reference. So with this, I would like to end this talk. So, bye.